Okay. It's taking a bit. Let's give it a second. Oh, I'm not sharing my screen. Fudge. Share screen. All right. Apologize for the hold up. This is a quick overview of the finite element method, and my name is Mikhail Sunchin. So the other day I watched a YouTube video published by the efficient engineer called Understanding the Finite Element Method, which I was blown away by the use of computer-aided manufacturing tools to calculate approximate solutions for complex figures. Essentially, the finite element method is a technique used in many engineering disciplines that breaks down the structure of a complex figure into a mesh of finite-sized elements to find a solution of any type of differential equation. Now, I know that sounds pretty boring, but one product in particular that extensively uses this method is a car. It's highly likely that the car you drive now has been used many times using this method to improve upon the car in terms of durability, functionality, and reliability. Tonight, I want to talk about what this method does and how it works, as well as its benefits and some applications of this method. But to understand what this method does and how it works, we must first talk about the origins of this phenomenon. The history and functionality of the finite element method should be understood. The origins of this method dates back to the 17th and 18th centuries, in which the mathematician Gottfried Leibniz made the first draft of a discrete variational method that contained element-wise triangular shaped functions. In 1851, Shellback, who was another mathematician, published his analytical studies of the draft, and then Rayleigh, who's another mathematician, published his numeric results of this draft. And this draft led to, and all three mathematicians together, this draft led to small advances in this method and the topic, which prompted many mathematicians to figure out approximate solutions for any type of complex figure simply by breaking it down into small and tiny elements. The University of Texas at Austin professor J. Tinsley Oden states that the finite element method is arguably the most powerful method for finding the numerical solution of boundary and initial value problems, which is characterized by partial differential equations. Engineers can use this method to reduce the number of physical prototypes and run virtual experiments to make improvements upon their designs. To run this type of experiment, a mesh is first generated, which contains millions of small and tiny elements that make up the overall shape of the structure. That way, we can see all the mathematical points of a 3D object, which we can now analyze. Then calculations would be performed for every single element, which would combine to make up the overall structure of the figure. Now with the quick overview of the history and functionality of this method behind us, we can now talk about its benefits. There are many benefits of the finite element method, in which one is an improved accuracy. In the past, many designs started out as sketches, which were then followed by prototyping. But in many cases, the prototyping phase sometimes overlooks the material parameters. However, with this method in use, this method requires designers to input all the material parameters, and which this would enable more precise and accurate modeling of all physical stresses in each structural unit. Another benefit is an improved design, generally. Instead of having to separate structural components in a system, this method allows the designer to model a whole complex structural system. And this is extremely beneficial and efficient because it would drastically increase the speed of the product development. And designer could also use this finite element analysis to determine how to stress in one part of one structural unit affects another part, another element or part, and another part in the structure. On the previous section, I talked about some of its benefits, and I also mentioned in the last section one application of it, which was structural engineering materials. But that's just one of many that I'm going to present to you. There are many real-world applications of this method. In the 90s, the technology and computing capabilities had become advanced enough that designers began seeing how this could be used in automotive designs. Big automotive companies such as GM and Ford began using this method, which in turn started to create designing cars at a faster pace, while also finding ways to make it more aerodynamic. EDAC Incorporated developed a full vehicle FEM model that tested for safety. They tested integrated seatbelts, which tested or evaluated any type of seat deformation and potential failure mechanisms from the results. Computational fluid dynamics is another type of finite element method, which was incorporated in the 60s by companies such as Boeing and NASA. With the increase in popularity of jet aircraft and with demands for better performance in military aircraft, new modeling and analysis problems started to surface. In 1964, NASA recognized that the future of structural analysis was indeed the finite element method. These applications of the finite element method are limitless. They're used in virtually any type of industry, whether it's in a lab setting, a factory setting, or an office setting. Now that I have covered the history and functionality of this method, as well as its benefits and some of its applications, I want to leave off with one last thought. The finite element method is not just something that's a computer program or a complex differential equation formula or whatever. It's the pathway to future growth in any sector of the economy. The ability to make efficient designs or systems that can improve safety, improve functionality, and is something that any company, wherever in the world, should implement in their system. Thank you.